Thank you, everybody, for being here. I'm super excited. So today I'll be talking about some fast immigration. And throughout this week, thanks to our amazing organizers, we've had tons of really, really cool talks, a lot of which have involved either having a large number of searchers there at the beginning, what I'm calling a sort of large N searcher situation, or systems where searchers are added in at some constant rate, possibly with mortality or other details coming in at the end. And while we're listening through all these talks, I think there are some natural questions that arise. For example, what exactly is are there any similarities between the sort of large N versus these fast immigration problems, right? Because if these guys are coming in really quickly, you get to a lot of searchers really quickly, surely they can't be that different. There's got to be some connection between the two. So that's one of the questions I'll be talking about. Beyond that, there's also some questions about like what happens when searchers aren't being added in at some constant rate, if they're coming in at some time inhomogeneous rate. So also the question of whether it's worth working with immigration processes. And I think this question will make more sense coming up later. And at the end, I'll talk a bit about searchers where you add searchers according to how many searchers there are. So it's a sort of population dependency. Okay, so I just argued why searching with immigration might be the same as large N. Here's why you might think that's different. So just so that we're on the same page, some brief description of these two models. For the large N, you have N searchers. You smack them down in some domain, moving around, IID, and you can write down the time for each searcher to find some target in terms of tau. They're all IID. You want to find the fastest, take the minimum, second fastest, second minimum, so on and so forth. What does immigration look like? There's going to be either 0 or 1 initial searchers, depending on which paper you're reading. Searchers are added to some position or distribution, again, according to some kind of rates, which might be constant, might not be constant. We'll talk about that later. And once again, we'll have searcher movements being IID. But you'll notice that the big difference is that instead of just having the taus here, now we have all these sigmas showing up. So if tau is the time for you to get from your starting point to the target, for immigration, you also need to take into account that it takes some amount of time for these guys to actually enter the system in the first place. And naturally, if you come in later, you're going to wait longer. And so if these guys are ordered, that means that they are not going to be IID. So here we're taking the minimum bunch of IID. Here we're taking a bunch of minimum over some variables that are correlated in some way. Why does that matter? Well, if you don't have IID, you lose access to some classical extreme value theory, which has some extremely powerful results. So for example, I'm sure a lot of you guys in the audience are familiar with this, but like the Fisher-dependent Denko theorem, if you take the minimum of a bunch of IID random variables and they converge to something when properly scaled, they end up with one of these 4 distributions. And so at least in the IID case or the large N case, it's natural that we end up with one of these 4 distributions, whereas with immigration, it might not be necessarily obvious. So are they the same or are they different? Well, let's take some results and compare them. So on the left column, I have some large N. On the right, I have constant immigration. Here's assuming a short time behavior. So this is basically the probability that your searcher, that a searcher finds a target extremely quickly. And it's growing roughly polynomially. And you can see in both cases that if you scale the fastest searcher, it goes to a Weibull distribution, one of the 4 distributions that was on the previous slide. And in the immigration case, you also get a Weibull, except instead of P, it's like P plus 1. Good enough. And if you look at the scaling terms, there's a P over here, there's a P plus 1 over here. you might conclude all you got to do is take your p's, turn them into p+1s, and it's the same story. Well, let's take a look at a different case. So whereas the first case where it grows polynomially can be applicable to, for example, random walks on networks, among other cases, the second case is applicable to, for example, Brownian motion. You still get that they converge to the same distribution, a gumbel, and these A's seem to look pretty similar. It looks like you can more or less just replace the N with the lambda. But a lot of these other details start getting a little bit more hairy. Like, for example, you have a P over here, you have a P+2 over here, which is not P+1. And you might be thinking, well, maybe in this place you just replace P with P+2, but here we have a P and here it stays exactly the same as P. So there are some similarities, but there are also some differences. And why is that? So the way that I like to think about it is through a coupling argument. And so here we have a picture. I can imagine over here we have our rate lambda process for immigration. And let's let these pink bars be the time that the searchers actually find the target, not the time that they enter. Okay, if we use Poisson thinning, you can split that up into multiple rate 1 processes, figure out where those hit the target, and you can either think of it as splitting these hitting times randomly amongst these three, or you can think of generating these three and then squishing them together to make your rate lambda process. Okay, is everybody with me so far? All good, all good. Okay. So I've done my Poisson thinning. Next thing I'm going to do is for each of these rate 1 processes, I'm only going to keep the fastest guy in each line. So this second searcher, I've X'd him out. This guy second, I've X'd him out. These other guys are all the first in their line, so they get to stay. And you'll see that even after I've X'd out these searchers, usually speaking, the kth fastest in both of these processes are going to be the same. Like if you look at the fastest on this line, that's the pink bar over here, they came first. The fastest searcher amongst these three, that's this guy, they're at the same spot. You can check with the second guy as well, second fastest, take the second fastest of the three, we have the green circle, they match up. We get into a little bit of a oopsie problem over here when we come to our third searcher. You can see the fastest of the third searchers here is over here, whereas the fastest of the third is down here. And that's because where this third searcher should have been got X'd out. And that, of course, is not very good if we want to compare these two processes. I just claimed that the kth fastest is kind of the same for both of these processes. But if your lambda is really big, the probability that your third searcher gets X'd out is really small, right? Because what needs to happen for your third searcher to get X'd out? It needs to land behind either the first fastest or the second fastest. If lambda was like 1,000, there's another 900 something more lines. That third guy's probably not going to end up on the same line as the first two. So the probability that the kth fastest in both of these processes approach 1, and therefore we can transfer results from this second process onto the first process. Everybody with me up to here?
So I was interpreting the purple bars as a time for immigration.
Yes.
Time for hitting the target. I got a little confused.
Yeah, sorry. Yeah, so the pink bars, these markers are all time where they actually hit the target,
okay.
not where they come in.
Okay.
Yeah.
Is that distribution a Poisson process? Because you're assuming it's Poisson, but I wouldn't have expected it to be. Is it a particular assumption that you're making? The distribution of the hitting times is Poisson.
Good question. So you can either think of it as you took the original just Poisson process and then you mark where they hit afterwards, or sort of retroactively. Yeah, you can also think of it with filtering, which we'll also talk about a bit more afterwards. It's a great question. Okay, great. So I made all this trouble of constructing the second process. What on earth is it good for? Well, if I want to find, let's say, the second fastest in this second process, I'm taking the second fastest out of lambda many lines. Each of these guys is IID. And so that tells us that the second process is really a large N process, right? Because each of these lines is producing one searcher. So you have lambda many searchers, and you're trying to find the kth fastest one. What's slightly different from just replacing lambda with n in the original process is that because these guys are immigrating in, the survival probability or the probability that you hit the target in some short amount of time changes ever so slightly, right? Like you can say that the probability that the target is greater than t is this exponential. You can get that from the Poisson, and then you can get this other short time behavior. So you take the original short time behavior, integrate it, and that gets you your new one. And so basically, the immigration is in some sense a large N process in disguise, just with a slightly different survival probability. Okay. So for our first question, basically the same, except slightly different survival probability. You can tweak that. And that also means that you can sort of transfer any results from the large N case up into the constant immigration and back and forth, however you feel like. Okay. So now let's talk a bit more about how searchers are being added, if they're being added according to this time inhomogeneous rate, which will also go back to Aaron's question a bit. And for this, let's think about the exact probability that K searchers have not found the target by some certain time t. I should clarify what I mean by time inhomogeneous immigration. Before, we were adding searchers at some constant rate lambda. Now we're adding them at rate lambda times some function of time. Okay, so if we think about an exact formula for the kth first passage time, well, we can also rephrase that as the probability that fewer than k searchers have found the target by time t. So if we can describe the number of searchers that have found the target before time t, if we can describe that distribution, we're good. Okay, and to do that, let's think about 3 questions, going up in complexity maybe. First question, if you have constant immigration, how many searchers are there at time t? Not worrying about finding a target or not at all. Well, this is immigration. You're coming in at a constant rate. That's going to be Poisson. You integrate up the rates. The rate is always lambda, Poisson lambda times t. Okay, so for constant immigration, how many searchers have found the target by time t? So this time we actually care about it hitting the target. Well, if you're coming in at this time, your searchers are coming in still at rate lambda, but only this fraction of them, the probability that you find the target before, if this is point S1, then this distance is t minus S1. If you can find the target before that time, then you're a successful searcher. So the rate of successful searchers coming in at this time is just lambda times this probability. And therefore, this is an inhomogeneous Poisson point process. To figure out how many guys have found the target, we just need to integrate up the rates again. And so that gets you to some of the previous expressions on the previous page. And I think this formula also showed up more than a few times in previous talks. Okay, so last part, we have time inhomogeneous immigration. How many searchers have found the target at time t? Well, instead of lambda many searchers coming in at this point, Now it's lambda times u of whatever that time point is. And so we can immediately write down that the number of searches that have found it is Poisson with rate that. So this is how many searchers are coming in, how many of them actually find the target. And so these are nice, basically one-line derivations that I find pretty nice. And since I haven't taught in a while, I'll leave it as an exercise to the viewer if you want to take the time inhomogeneous stuff and apply that over to the coupling argument that we went over. Okay. That's that. So searchers are added with the time inhomogeneous rate. Your methods and results in some sense are pretty similar to constant immigration. You get this slight tweak once again. And by the first point, therefore, it's also fairly similar to methods and results for logic. Okay, so with these previous questions, I've sort of made it a point that you can sort of transfer these results from large N into constant immigration. At this point, you might be thinking, oh, then there's absolutely no point to thinking about immigration problems. I should just always work in large N. So is it actually worth working with immigration processes at all? I would argue yes. So let's give a quick example. Let's say we're dealing with these sort of bounded velocity like PDMPs that have come up both in earlier this morning and in previous talks. And let's say we just want to find the mean fastest, mean kth first passage time. Well, short time behavior, there's some probability that you find the target at some minimum time, and then there's some distribution that comes after that time. And if we do some scaling of the times, you either find the target immediately or you find it a little bit later according to this x tilde distribution. Okay, how am I going to go about finding this mean first passage time? Well, the number of searchers that have found the target before time t, we can use the results on our previous slide, our lovely one-liners, and say that it's Poisson distributed with mean, again, rate of entry, and then probability that you actually find the target if you enter at a given time, which if you expand this out a little bit with this definition, gives you this expression. We can generate the kth first passage time by taking a rate 1 Poisson point process and doing a time scaling. So we can take our, this always comes out so nice on text, but I never really know how to say it verbally. The math calc-t, which if you care about the actual sequence, you can generate from your Poisson point process. If you only care about the distribution, you can pull it from an Erlang distribution, which is just a gamma distribution where one of the parameters is an integer. And you can solve this expression where this mu is our number of searchers, average number. And so then if I want to find the average first passage time, well, I just take the inverse of this Erlang distribution. And looking at this expression, we can pretty quickly guesstimate the a rough approximation for the inverse. And that gives us a two-term expression. You'll notice that this integral over here goes up to something divided by lambda. So that's going to get really small. So at this point, all you got to do is plop in your short time behavior for your expression. These t's are all Erlangs, so you know exactly what that distribution is. Plug that into Mathematica, and you're done. And so this is like a one slide. You can do the problem, pretty much everything you'd want to know. And so, is it worth working with them? Yeah, I think you might lose the machinery from the extreme value theory type of stuff, but you do gain a lot of machinery from working with these Poisson point processes that you can leverage. Okay, and my last question, what happens if you add searchers based on how many searchers there are on the system right now? And for that, I have an example using what I'm calling Yule immigration. Basically, it's a pure birth process. The more searchers you have in your system, the faster your next guy comes. And it's proportional to the number of searches that you have. And this is why I said 0 or 1 earlier. You do kind of need one searcher to kick off things for Yule immigration. It would not be an interesting process if you started at 0. Okay, and why am I thinking about this process? Well, a lot of processes, at least initially, grow kind of exponentially. So you might be thinking you have a logistic number of searchers. That's okay. If you trim off the later parts, it looks more or less exponential. And so maybe this will give some intuition on what other processes might look like. And after a non-significant amount or a somewhat significant amount of algebra, you can show that under these previous short time behaviors that we talked about, you can get that when properly scaled, the kth first passage time approaches this distribution. And if you let k equal 1, so you're thinking about the fastest first passage time, you get a logistic distribution. And I was extremely happy to hear this, because when I was working on the constant stuff, I was like hoping that I wouldn't get like those Weibull, Gumbel, same old distributions. And so I was like, yes, finally, I got something that isn't one of the large N distributions. This is clearly something different. Until I looked on Wikipedia and I learned that the logistic is a difference of 2 Gumbel distributions. And so the natural question now is, why on earth is it the difference between 2 Gumbel distributions? And here's a sort of heuristic sketch for why. If you have a very large lambda, well, the number of searchers at a given time, it grows exponentially, e to the lambda t, but there's also some amount of stochasticity in the beginning, right? Like you can get very unlucky and the process takes a really long time to take off, or you might get really lucky, big burst at the beginning, your process goes up very quickly. And yeah, you can show rigorously that you can put a random variable here, v, which is just an exponential random variable with rate 1. And what I'm going to do is I'm going to take this v and drag it up there. Why on earth did I do this? Well, if I drag this v up here, the way that I want you guys to interpret this expression is that we have this e to the lambda t, this sort of expected mean behavior, and then we have this 1 over lambda natural log v, which in some sense is like a random time shift away from the mean process. Okay, so if you believe me up to there, we can write down again the probability that the scaled form is larger than some x. What I'm going to do is replace that. Oh, that should be a 1. My bad. If you replace that with the mean behavior and then this time shift, then you might guess that these 2 expressions are roughly equivalent, give or take. And then if I plug in the value of a sub lambda, which is 1 over lambda, do some shuffling around, you end up with this, this scaled version of the average case minus the natural log of our random variable shift, our exponential. And it turns out that if you take the natural log of an exponential random variable, you get a Gumbel distribution. And that just comes out from your introductory probability class. If you do some more algebra, you can also show that this scaled mean behavior goes to a Gumbel. And so the probability that our scaled random variable is greater than x is a Gumbel coming from the mean behavior minus a Gumbel coming from this random time shift. And so that gives you Gumbel minus Gumbel, gives you a logistic. And so for conclusions, these results for large N first passage time problems can be generalized to results for fast immigration using this sort of coupling argument. You can also work directly with the immigration process instead of trying to lift results from large N, taking advantage of the power of Poisson point process machinery. And also how you add searchers can matter. if you have these sort of population-dependent rates, that noise can actually knock you away from the usual Weibull-Gumbel distributions. There's a link to my webpage. There are like 3 papers that are relevant to this. One SIM applied math, one in chaos, one went on the archive earlier this week. Most of the work was done at the University of Utah during my postdoc with Sean Lawley, and a tiny bit of it was done at Princeton, where I am supported by my patron, William H. Miller III. And thank you all for listening.
Questions? So you thought about that the immigrating particles have a different distribution from the other ones. Could you do something where there's multiple types of distributions going on?
If you have multiple types of distributions going on.
You have n initial walkers, then the ones coming in have a different distribution. What could you do in that scenario?
That's a good question. I think you'd end up more or less just comparing the minimum of several different processes, depending on which type of speed is coming in, would be my guess. I think you could probably crack the problem that way.
And yep, question over here.
Do you think the large lambda and large n correspondence would hold if we fix, let's say, the mean inter-recruitment time to be 1/lambda, but the distribution to not be exponential? So it's not a constant rate immigration, it's not a time inhomogeneous immigration, but it's a renewal process where there's a distribution, I draw a time, recruit, and then I draw another time from that for the next recruitment.
That's a good question. I think at the very least, my coupling argument would break down, I think. I don't think you can do the same filtration kind of tricks, unfortunately. That's a good question. I think you'd have to take it at an ad hoc basis, depending on how that renewal process works out. That's a great question, though. Thank you.
Samantha?
Can you speak to what extent you'd expect this UL immigration stuff to carry over to like UL branching?
Yeah, my guess is that if you have just like a generic branching process, and you assume, or like a birth-death process, and you condition on survival, not everyone dying out, my assumption was that it would be the same. You get these sort of, you can write down a pretty similar looking result for branching processes, except instead of exponential rate 1, it has to do with the birth and death rates instead. So my expectation is that it would more or less qualitatively carry over.
Okay, thank you, Ray.
Thank you.